because Calc 1 is, it might be like a fond, distant memory at this point. Where it's like, oh, I miss the days of Calc 1 when everything made sense and it was all...
Oh, last semester.
Yeah. It's like, this is great. And then Calc 2 happened. And here we are, you know.
Calc 2 makes
So,
sense.
what's that?
Calc 2 makes sense.
Generally, I like to think it does, but
I think it uses the look.
that could be fun.
It was harder to grasp.
Definitely.
This is just like Calc 2 in three-dimensional stuff.
Exactly. And I think, in all honesty, I think the hardest part about this stuff is visualizing what it is you're supposed to be looking for.
Yeah.
You know, because if you don't know what the equation negative x squared minus y squared plus 2x plus 6y minus 11 looks like in 3-space, it's like, you know, going back to Calc 1, I had an idea going into every problem whether there was going to be a relative max, relative min, point of inflection, what kind of concavity I was looking at, and all that good stuff, just because I could pop it in my calculator. If that's assuming I didn't know what the function looked like to begin with. If I didn't know, I would just pop it into my calculator, take a quick look, and say, okay, this is what I'm up against. Now I just got to make the math work itself out. Here it's a different story because you may not have a good visual sense of what is going on here. Right?
We'll
So,
calculator in 3D.
or, yeah. So, anyway, these properties and rules come in probably more handy than you would expect. Right, just because of that idea. Right, so we call f of AB a local maximum if there's an open disk R centered at a point AB, for which that f of AB is greater than or equal to f of x sub y, x comma y. What that means is that you have a particular point that's higher or equal to every other point on the surface, right, or at least on that interval. All right, same idea for a local minimum. Right? Both are called local extrema. Critical points. Remember those from Calc 1. The point is a critical point. If AB is in the domain of F, it's very important. I mean, it's kind of stupid, but like, yeah, it would have to be within the domain in order to be a critical point. That goes back to continuity implies differentiability. So if you don't have a continuous point, if a point doesn't exist, yeah, the derivative may be equal to 0, but if there's no point there to begin with, then you're not really getting anything meaningful out of it, all right? So what we get from this is the partial with respect to x has to be equal to the partial with respect to y, which has to be in turn equal to 0. Or one or both of them, one or both of the partials do not exist at that point, all right? So the point itself has to exist, but the partials don't have to exist. All right, so you plug in a, b to your original function and you get undefined, all bets are off. You're not looking for a critical value. You get something that exists, you take your partial with respect to x, partial with respect to y, plug those numbers in. If you get both of them to be equal to 0, or either of them to be non-existent, then you're looking at a critical value. All right, and we know from Calc 1 that critical values lead to local extrema. All right, there are starting points for determining whether there is an extreme value. Condition for local extrema: if f of xy has a local extremum at AB, then AB must be a critical point of that. All right, so that's what I just said. All right, now saddle points, that's new. So you got a whole blurb here. It's a saddle point if you have a critical value, critical point, and well, other things. So if every open disk centered, I really have to explain at some point what these open disks mean, but it really is just the idea that you're not talking about a particular interval. You know, in Calc 1, it was like on the interval A to B, you can go from 2 to 3. But in 3-space, you can go that distance in every possible direction. And so what it does is it creates a circular region. All right. So that's really what that's getting at. But I'll illustrate that at some point down the line. All right. Centered A and B contains points x, y in the domain for f, for which f of x, y is less than f of AB, and points x, y in the domain of f for which f of xy is greater than ab. All right, what does that mean? It means it's neither a maximum nor a minimum. All right, it means that there are points above it and there are points below it. It kind of has the same sort of feel as an inflection point, but in 3 space. Right? It doesn't necessarily mean a transition of concavity, but it's along those lines where you'd have a critical value, you'd test it, maybe you do a sign chart, and then you'd say, oh, well, that critical value is not a local max or a local min because there's no sign change around it. So what is it? Well, maybe it's an inflection point, so you take the second derivative and go that route. All right, so this is the case of you got a critical value, you tested to see if it was a local max or min, it turned out it wasn't one of those. So what is it? We call it a saddle point. All right. So how do we find these things? Well, sometimes it's just a matter of doing a little bit of algebra. So critical points for the function. So first off, I would test for continuity. The test is not something formal that you need to do. You just look at it. Is there any bad value of x or y? No, it's perfectly fine. So we can get into our partials. So partial f with respect to x is going to be 2x plus 2. Partial, poor quality partial f with respect to y. Oh, sorry, it was negative 2x plus 2. Negative 2y plus 6. All right. So again, just going back to the definitions, if you have a point for which the partials are equal to 0, that would give us a critical value. If you have a point for which the partials do not exist, then you would also have potentially a critical value. So what I can do is set each of these equal to 0. Classic Calc 1 maneuver. When in doubt, set it equal to 0 and solve. All right, so I got an A and a B value. All right, so we're looking for relative extremum. At 1, 3, f of 1, 3. Figure that out in a second. I'm putting a question mark there because we don't know for sure. That's the investigate part. All right, now, based on the picture, it looks like maybe there's something there. We could plug in the 1, 3 for x and y. I'll just kind of do it right above the equation. Negative 1 minus 9 plus 2 plus 18 minus 11. So negative 1? No, that's not right, is it? 7, 9, 0. Is it? Is it? It's negative. Oh, look at that. All right, so if this is going to be a relative extremum, then this would have to be the largest number. Based on that diagram, we know it would be a maximum. Right? There's more to it than that because you can't just rely on the picture. But for now, I mean, we have the picture, we might as well take advantage of it. If this is the largest value available, not only do we have a relative max, but we also have an absolute max. All right? So what can we do? Well, we can do a couple of things. One thing would actually be to try to get this into some other form. So f of xy, again, I'm going to rewrite the whole thing. I'm looking at something that is definitely a quadric surface, right? What that means is that it's a conic section that's just projected into 3 space. So it has the look of, you know, when you see x squared, y squared, you're thinking ellipse or hyperbola, maybe a sideways parabola, but they're both squared, so it wouldn't be that, right? It could be any one of those figures. So a good strategy would be to use completing the square to get it into a standard form.
Does it matter if it's relatively extremum or extreme?
In this case, because there's only one, it would be an extremum.
Oh, okay.
Yeah, but I mean, if you use extrema instead of extremum, nobody's taking off points for that. I shouldn't say that. I'm sure there are many people who would take off points for that. I'm just not one of them. Nah, even there, I don't even think so. Everybody. No, B plus, sorry, anyway. All right, so we would complete the square here. So I am going to cut the b value in half, square it, and then divide by the leading coefficient. So it's going to be a -1. I did. A good question.
Did you record last session?
The one I wasn't here for?
Yeah.
No.
So Mike's still the
That being said, I just gotta sit down and do it, but I have the video from last semester. I'll post it up so that you at least have it. So anyway, I'm subtracting 1 here. You can't just subtract 1 from an expression and just say, oh, I wanted to do that. If that's the case, why not just add an x squared, subtract a 2x, add a y squared, subtract a 6y, and add an 11 and call it a day? You know, you can make it all 0. You know, if you're going to break math rules, break them like with authority. So, yeah, I got to correct for that. So I'm subtracting an arbitrary 1 here. Arbitrary. It's coming from the completing the square process. But I have to correct for that by adding a 1. Same idea here. I have to subtract a 9 because the b value cut in half becomes 3. Squared is 9. Divided by the leading coefficient is -9. But then I have to correct for that. All right, so I have a GCF over here. I'll pull it out. X squared minus 2x plus 1. I have a GCF over here, also a -1, so minus y squared minus 6y plus 9, and then minus 1. All right, -11 plus 10. All right, so it's like, all right, what's the benefit of all this? All right, just stay with me. Negative x minus 1 squared minus y minus 3 squared minus 1. All right, this is actually the justification for why -1 is the largest number, the largest z value. Again, just I go back and forth. F of x comma y is the same z equals. All right. So what I'm doing here, and I'll write it slightly differently. I'm taking -1 and I'm subtracting something that's positive. And then I'm subtracting something else that's positive. This is a positive number. This is also a positive number. Therefore, the largest z has to be equal to -1, because if I, just pick any 2 positive numbers, start with -1, and then take 2 positive numbers and subtract them from -1, you're going to get something that's more negative. All right. If I made it a 2 and a 3, -1 minus 2 minus 3 is going to give me a -6. That's smaller than the -1. No matter what I plug in for x or y, I'm always going to get something smaller than or equal to that -1, because these two could zero out. The only time they ever zero out is if x is 1 and y is 3, which is what we came up with as critical values before. So those critical values are justified as being the location of a relative extremum, specifically 1, 3, -1. Question.
We were able to do that because we made this look like an open disk, so that's like the formula for a circle, so we could say it's going down those are positive values. What if it didn't look like an open disk? What if it was some random equation?
That's the next part of the
ln
lesson.
of x.
Next part of the lesson.
Okay.
Yeah, there's properties and rules that come into play when this doesn't work. Because this is ideal. Okay, it doesn't look like it's ideal. But this is the best case scenario. Now, you just kind of wrap your brain around that idea for a second. Like, half a page worth of work is the best case scenario when it comes to this.
And we got the 1, 3, -1, and we didn't plug it into the derivative because it's 3D, correct?
We didn't plug it into the
I
derivative.
remember in Calc 1, we plugged it into the derivative to find out.
Oh, like in a sign chart?
Yeah.
Yeah.
Find the x and the y.
Yeah, we wouldn't need to do that. Yeah, we're going to use a different approach in a sec. All right, so,
Oh no.
yeah. Critical points of the function cosine x sine y. All right, so if you were ever wondering what the equation was to generate those like egg crepes, you know, like you put eggs in them, that's what it is. Or mattress toppers, right? Yeah, it's cosine x sine y, or cosine y sine x. You know, all sorts of possibilities get you the same thing.
Or
Yep.
cosine x, cosine y.
Or cosine x cosine y, you know, sine x sine y. You know, so all sorts of things. All right, so tangent's fun.
Which looks like a series of like cones and
Like
stuff like that. Yeah.
So critical point, because I think we'll all agree when you look at it, cosine, sine, they're both continuous everywhere, so we're not worried about that. So derivative. So partial with respect to x. So I'm going to hang on to the sine of y. Cosine x becomes negative sine x. Partial with respect to y. Hang on to the cosine x. It's going to be cosine x, cosine y. All right, so I'm going to set those equal to 0 and solve. So we have two factors, set each one equal to 0. You can sine x equals 0, sine y equals 0. Now, this is an or situation. I'm just going to tuck a little or in there. All right, maybe I'll do that in a different color so it actually stands out. Because it doesn't have to happen simultaneously. In order to get the partial with respect to x equals 0, either one of these needs to be equal to 0. If they're both equal to 0, great, but they don't need to both be equal to 0. All right, same idea for the cosines. All right, so cosine x equals 0. Cosine y equals 0. All right, so think about the unit circle, and you think about instances for which the sine function is equal to 0. That happens along the x-axis. So we're talking about x has to be equal to 0, pi, 2 pi, and so on. Y has to be equal to 0, pi, 2 pi, and so on. Cosine has to be equal to 0. Oh, I already wrote the cosine. pi over 2, 3 pi over 2. Maybe some negatives if you want, but let me just focus on the positives. 5 pi over 2, and so on. Same thing for the y's. All right, so I tucked a little and symbol in there. Actually, I'll do that a few steps of the way here, because they have to happen in conjunction with one another. The partials will never be undefined, so I'm not worried about where they would fail to exist. I'm only worried about where they'll be equal to 0. All right, so I need to pull from these values that would allow this partial and also this partial to be equal to 0. All right? So now it's just a matter of itemizing everything. All right? There's a lot of stuff to go through here, and so it's just a question of do I have everything that I need? All right? So now the one issue here, or one main issue, is that each of these functions consists of both an x and a y. All right? So we just got to be careful that we're not going to run into any domain issues. And when you're dealing with sines and cosines, that's not typical. It's not something you really need to worry about. But just for other types of problems, you want to be mindful of that. All right. So as far as ordered pairs are concerned, 0, 0 will do it.
I'm sorry, does that mean that any combination of any x and any y will result in a critical value?
Not necessarily. So that's what we're going to do. We're going to go through each one of them and test them out and make sure that they both lead to both x and y values that I choose will lead to both partials being equal to 0. So, for example, 0, 0. Well, 0, 0 and whatever the z value is associated with that. So, I know it's going to work here. If I plug in a 0 for each part, it's going to give me a 0. If I plug in a 0, because once I've decided that I'm working with 0, 0, that's going to be, I mean, it could be good or it could be an issue. On this side, it's perfectly fine. But if I'm going with 0, 0 here, it better work over there because they both need to be equal to 0. So if I plug in a 0 for cosine, I get a positive 1. In both cases, I'll get a 1. 1 and 0 are not equal. So this would actually be a bad ordered pair, right? Because it needs to work for both. All right? So then I would try 0 pi. All right? So if I plug in a 0 and a pi for that, because it came from this set, we know it's going to be fine. But will it work over here? If I plug in a 0 and a pi, that's no good. All right? That's going to give me the same issue. All right? So it's not going to work for both. If it doesn't work for both, it's no good. It has to make both partials equal to 0. All right? So then 0, 2 pi, no reason to expect anything else will come from this. Right, so then we start mixing and matching between the two functions. All right, so we take an x from one set and a y from the other. All right, so this one didn't play out, so I'll get rid of that. So then what I would do is I'd go with 0 and pi over 2. 0 for x, pi over 2 for y. All right, we know the 0 is going to be fine over here. The pi over 2 is going to be fine over there, so we're good. All right, so I'll take an x and pair it with each one of these y's. Any one of these x's along with any one of these y's will be perfectly fine.
And then vice versa, right?
And then vice versa. All right. So we would have x of 0, y of pi over 2, 0, 3 pi over 2, 0, 5 pi over 2, and so on. So instead of writing that, let's just pare it down to say 0, comma, pi over 2 plus pi k. All right. Now, if we know that that's also going to work for the pi, 2 pi, and so on, then we could even extend it further by saying, all right, wait a minute. It's really not that as much as it's saying, because we can focus on this guy and say it doesn't have to be just that. It could be any of these. So we would say 0 plus pi k, comma, pi over 2 plus pi k. And then the z's associated with all of those. All right, so I'd have to write, this is ugly, but f of 0 plus pi k, comma, pi over 2, sorry. No, actually, no, it was right. Pi over 2 plus pi k. Now, here it's only asking us to investigate the critical values. It's not asking us to state what if any, the max or mins are. Because there's also the possibility, just to make this as mind-bending as possible, some of these might play out to give us a max, and some of them may play out to give us a minimum, right? And how we juxtapose them might impact things, but that's beyond the scope of the question. All right, so the other way around would be to say this group of x's with that group of y's, in which case I would say pi over 2 plus pi k, 0 plus pi k, or just pi k if you want, and then f of all that. All right, and so just to talk you through the remainder of it, because honestly I don't remember what I put in my answer key online, but I might have gone a little bit further. The idea would be, if you needed to determine a max or min, you would plug them back into the original function. Because these are periodic, which means that once you've established what a maximum is, it's going to be the same, it's going to propagate throughout. So let's say, for example, I wanted to go with pi over 2 for x and 0 for y. If I do that, then I'm going to get, I'll get a 0, right? In the original function. All right, so that would actually be a saddle point, right? Because that's neither max or min, so we would call that a saddle point, right? If I did, let me see if I can find one that works. I need one of these guys. Actually, they're all going to be, all of these are going to give me saddle points. Oh, no, this set will give me Extrema. Because if I put a cosine of 0, that'll give me a 1. Sine of 1/2 would give me a 1. So at 0, 1/2, I'll have a z value of 1. 0 pi over 2 is what I meant to say. I'll have a z value of 1. If I did pi and 3 pi over 2, same deal, I think. Negative, negative, so positive. Yeah. So we would be living with maximum values there. But you could test them all out, you know. But again, beyond the scope of what the question's asking, because there's other ways to do this that don't involve us testing all possibilities.
Well, I was going to ask that without looking at GeoGebra, how do you know that the max value would be 1? I mean, in this case, because it's cosine and sine, it repeats itself.
Right.
But like,
once you've come up with your array of critical values, you know that the max or min has to come from that set. So then, worst.
Tons of sets.
Right, but there's the periodic nature of it. Like when you're dealing with something like this, you're not going to have too many possibilities. But when you're dealing with something like this, yeah, you have a ton of possibilities, but many of them repeat themselves. So once you've gotten a full collection of all possibilities, you figured out what X and Y combination gives you a positive one, gives you a 0, and what gives you a negative 1, then you've accounted for pretty much everything. And so you could just move on from there. All right, numbers 3 and 4 are much easier, so I'll put stars on those. The next class I think is going to be a star-studded class, because I have some star problems from the last class I taught, and then these new stars. Test. All right, in Calc 1, that didn't strike fear into the hearts of people everywhere. The idea of a second derivative test. You just take the derivative a second time. But in Calc 3, we know second order partial is like, we want second order partial with respect to X or Y or mixed second order partial. Oh, geez, which one do you want? So, very procedural. The issue, though, is it's not a short procedure, right? And not short in actually reading through it, and not short in carrying it out. Suppose that f(x,y) is continuous second order partial derivative in some open disk containing the blah, 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 blah. All right, so you have critical values. The continuous second order partial derivatives, that's like a throwaway statement from Calc 1, but here it's so important because what it means is that your second order partials are interchangeable. All right, so partial xy is the same as partial yx, right? Because it's continuous second order partials, right? If it were not the case, then this all falls flat, all right? We define the discriminant, all right? So we get our critical values, still got to do that, but we define the discriminant by this formula. Second order partial with respect to x, then y, then the mixed. We'll talk about where that comes from next time. Once we get that value, it's kind of like discriminant sort of from quadratic formula, where you have conditions associated with the type of value that you have. If your d is positive, and so is your second order partial with respect to x, then you have a local minimum at AB. If only the d value is positive, but the second order partial with respect to x is negative, then it's the local max. If you have a negative d, this is the one that you're hoping for, because that means, well, actually these two, kind of. 3 is really the one you're hoping for, because it's the one where you could draw a conclusion by doing the least amount of work. Your d value is negative, then that means there's a saddle point. It's neither maximum nor minimum. Critical value doesn't lead to a max or a min. The d equals 0, it depends on the question. If it says use second order partials to draw a conclusion about or classify the critical points, then that's fine. But if your objective is to find the critical points and then find extrema, and you get a d equals 0, there really is nothing more frustrating. Because what that means is, well, maybe it's a max, maybe it's a min, or maybe it's neither. I can't conclude based on what we've done, which means I wasted all my time doing that, which is brutal. All right? So definitely something to be avoided. But anyway, let me find my first order partial with respect to x. 4x cubed minus 4y. And my first order partial with respect to y. 4y cubed minus 4x. All right. Now these have to be equal to each other and equal to 0 in order to have a critical value, right? Or if either of them don't exist, but so far continuous differentiable all the way through. So I'm going to set it equal to 0. I'm going to clean it up. I'll make this y equals x cubed. All right, the other one, same general idea, except it's x equals y cubed. All right, so we have a relationship here. That's something. Doesn't seem like an overly meaningful one until, well, this is the geeky math teacher inside of me. Well, inside of me. That's who I am. So it's this and that. So that's the definition of a system of equations. Two equations that are true simultaneously. So I need y to be equal to x cubed at the same time that x is equal to y cubed. If that's the case, that allows me to substitute from one equation into the other. So I can replace, for example, the x cubed here. I'll replace the x with a y cubed and make it y equals y cubed cubed, which means y is equal to y to the 9th. All right, now just be careful because Algebra 1 students do this and Calc 3 students do this too. You can't just divide out a y. You're going to lose a solution. All right, so bring over the y to the 9th minus y equals 0. Factor. And solve. You get y equals 0, y to the 8th minus 1 equals 0, which means y to the 8th equals 1, which means y is equal to plus or minus 1. All right, so we have 3 potential y values, which correspond to 3, well, possibly 3 potential unique x values. All right, so x is equal to y cubed. So if x is equal to y cubed, and we have these 3 y values, then we would get ordered pairs. If I plug in a 0, I get a 0. If I plug in a 1, I get a 1. If I plug in a -1, I get a -1. And these would all have z values associated with them. But again, instead of plugging and chugging away, well, the first one I can do. 1. Well, actually, I guess I could do them all, because these are easy numbers to work with. So 2 minus 4 is -2, plus 1 is -1. Two, so it's same deal?
Yeah, same deal.
Same deal, right? All right, now it's hard to see this diagram, but it does look like kind of like a pair of pants, sort of. So it comes down and then it goes up. I'm not going to describe what that area is. And then it comes back down to the other pant leg. And then, so you have what appears to be a couple of minimum values, and then up in that area, that could be a maximum, or it could be a saddle point. So, yeah.
But I'm sorry, what would be the maximum? Or the minimum?
These two.
But without that picture, that's my point. That's like...
That's why we investigate using this approach. Because if you don't have the diagram, then you can't even go by that. So at this point, if that diagram were not there, I'd look at this and say, I have 3 possible coordinates that could represent 3 possible things. Min, max, saddle point. I don't know what's what. All right, so what we do is we figure out the discriminant for each one of them. All right. So I need my second order partial with respect to x, which requires me to see my x, 12x squared. Yeah, you just got to dial back your font. I mean, I figure if I spot you the first 100 pages and notes, or you can go to notebook pages every once and again. F of yy, f sub yy, that's going to be 12y squared. So I need, for each of these x, y pairings, right, I also need the mixed second order partial. So f x, y. So I'll take my x model and do it with respect to y, which is a little bit easier, a lot easier. It's just a -4. So that's nice. All right, so again, I'm going to evaluate each of these for each of the coordinates and see what my d value is. All right, so I'll do it right here. Oh, sorry. So plugging this in for x and y as applicable. Right. So 0 times 0 just trying to be able to point to the formula. So plugging the a, b values into the second order partial with respect to x, it doesn't call for a y, so I only have to plug in the x value. The f of y, oh, that should have been a, no, it's still a 0, because I'm plugging in a 0 there. But then we're going to subtract the -4 squared. So subtract -4 to the second power, and that's going to give me a 16.
Minus 16.
-16. All right, so then I'll do the same thing for 1, 1. And then we'll do the compare and contrast all in one shot. So 12 times 12. And it's going to be the same deal because the second order partial with respect to y, the mixed partial, is still -4. It's constant. So we're still going to have a subtraction of 16. So 144 minus 16 is what, 128? And then I do the same thing for -1, -1, and that's going to give me the same result, right?
Yeah.
All right. So, looking at my conditions, I always go for the saddle point first. All right, saddle point is the easiest one to identify. If your discriminant is negative, then you have a saddle point. All right. So my saddle point is at 0, 0, 1. In the case of the second two coordinates, I have a positive discriminant in both cases. So it's really just going to come down to my second order partial with respect to x and whether it's positive or negative. So I extend upon this and I evaluate my second order partial for 0, 0. Oh, we already did 0, 0, sorry. That's the saddle point. And I wrote 0, 0 again like a fool. Can't get out of my own way sometimes. So that's just a 12. That's greater than 0. So we now know that at 1, 1, -1, what happens when my second order partial is positive? What do my conditions tell me?
Either minimum or
It's minimum.
Yeah.
Local min. All right. And then when I plug in -1, -1, I get a positive again, right? So it's still a local min. Now the diagram helps, definitely. And I pick and choose my battles when it comes to that. Sometimes I want you to have a diagram on a test to refer to, and then sometimes I don't, right? Because if the diagram gives away everything, then that's not what I want. You know, like if I'm asking you to find the volume of a sphere, but I don't want you to know it's a sphere, then I'm defeating my own purpose if I give you a nice picture of a sphere on the test, right? But in this case, I'd be more inclined to give it, because once you get, first off, you can see that we have z values of 1 and -1. These two are at the same level, at the same z level. So what's true for one is probably true for the other. It's just a question of whether this 0, 0, 1 was a maximum or a saddle point, all right? So what's happening is, I mean, we can't see up in the nether regions there, but if we could, we would see that this point has values of z that are both higher than it and lower than it, all right? So there's a transition that does not allow for it to be the highest point, to be the king of its particular hill. Question? They're both local mins, yeah, because we have two legs here. So this one is the local min on this side, and the other one is the local min on the other side.
Your first two I parts, it's asking us to take this, find local min and max. Asking us to do it with f of the double derivative of x. Would we do that for y as well? If it didn't happen that our x to the power 4 is also our y to the power 4.
For which part?
See how we find our local min and max? We
The
plug it into
rules,
the
number
f,
1 and
x,
2.
x.
Oh, you're talking about these bad
What
boys.
do we do with y?
We don't bother with the
The
second order partial with respect to y.
Okay.
Yeah. We only look at it with respect to x. All right, so I'll put a star on number 7. That's actually a pretty tricky one. It does, I guess it doesn't have to be, but it requires a different way of thinking about it. So if you struggle with that one, I understand. I'll definitely take some time and go over that on